In this video, we're going to talk about factorization into irreducibles in Z adjoint X. And in particular, we will show that every non-zero polynomial in ZX factors into irreducibles in ZX. Now, one thing we have to allow here is that it's possible for a polynomial, and I'll just give an example here. It's possible to have a polynomial that's constant in ZX and that is a unit. And so its factorization in the irreducibles is not going to be that interesting. Just factors into 1. And we count that as an irreducible factorization. No, 1 is not irreducible, but we think of that as an empty product of irreducibles. So let's write that down there. So that's an empty product of irreducibles, since this is already a unit. Okay, so that's a dull example. Here's a better example. Suppose we begin with some polynomial like 2x cubed plus 2x squared minus 8x minus 8. So here's how the strategy of this proof is going to work. I look at this polynomial. First of all, I see whether there is any content to it. In other words, whether there are any common numerical factors among the coefficients. And there is a 2 in common, so I'm going to factor that out first. So this whole thing is equivalent to 2 times x cubed plus x squared minus 4x minus 4. And now I look at this. Now I have a polynomial here, cubic, content 1. It's primitive. So now there's no other numerical factor I can factor out. However, I'm going to look at this and say, well, is this irreducible? If it is irreducible, great, then we're done. This is an irreducible factor because 2 is a prime number, and this is an irreducible factor, except, well, this is not an irreducible factor. It can be factored further. So the strategy of the proof is, if it's irreducible, then stop. If it's not irreducible, then it should factor into some other pair of non-units. So in this case, those non-units are going to be x plus 1 times x squared minus 4. And I just factored that by grouping. I observed that this was x squared, x plus 1, minus 4, x plus 1. And then from there I was able to factor out the x squared minus 4. Okay, so now I look at this and I say, well, are these irreducible factors? This is irreducible, so that's great. This is irreducible. Great. Is this irreducible? No, not irreducible. It is reducible, which means we have to continue on further. So we end up with 2x plus 1, x minus 2, x plus 2. And at this point we are done because all of these are irreducible. So now we're done because we have factored this original polynomial here, the one marked with a star, into irreducibles. And that's a very algorithmic approach. You just start with your polynomial, factor out any common numerical factors that you see, and you know that any common numerical factors will factor into primes because we know that the integers factor, in fact, uniquely into primes. And then you take this other part, this primitive polynomial here, and then factor it as far as you can go. And then when you can't factor anymore, that means that you're done. That means that all of your factors are irreducible. So, like any algorithmic proof, there are two things I want to pay attention to. One of them is the fact that we're not going to write the proof exactly as an algorithm. Instead, we're going to use induction. So the question is, what are we going to induct on? And that's a good thing to think about. You should maybe even pause the video and think about how we would set up an induction proof here. And then the other thing is, any algorithmic proof needs to rely on the algorithm being able to stop eventually. So what is it about this process that requires this algorithm eventually to stop? And actually that gets built into our induction. If we set up the induction right, we won't need to worry about that explicitly too much. It's just we need to think about what it is we're going to induct on here that's going to allow us eventually to get down to irreducible factors. All right, so those are a couple of things to think about. Let's see if we can write the proof. So we will begin the proof the same way that we began the algorithm, which is we're going to start by taking out any common numerical factors. So let's let f of x belong to z of x and assume it's non-zero. All right, first, we let D be the content of f of x. All right, so D is the GCD of the coefficients of f of x. Then we have f of x equals D times P of x for some primitive polynomial, not necessarily irreducible, but some primitive P of x belonging to Z of x. All right, so far so good. So now we're going to start working on P of x. We will show that any primitive polynomial in Z of x factors into irreducibles. Okay, so now we're sort of jumping into a lemma here because we're going to prove this for all primitive polynomials, and this is where we're going to use induction. So we're not going to fix our attention necessarily on P of x itself. We will come back to that at the end of the proof. Okay, so we're going to prove this by induction on the degree of the polynomial. All right, so the base case. So technically there are primitive polynomials of degree 0, so we should address that first. I'm going to call this Q of x because I'm going to leave P of x to represent the primitive polynomial that came out of this algorithm here. So we're going to let Q of x vary over the primitive polynomials. If degree of Q of x is 0 and Q of x is primitive, well, okay, so that means that the GCD of the coefficients of Q of x is 1, but Q of x only has the one coefficient, its constant coefficient. So if that constant coefficient is anything interesting, that content is going to be greater than 1. So that means Q of x has to equal plus or minus 1. Okay, that's really two separate possibilities there. And either way, Q of x is an empty product of irreducibles. I'm allowing here, just a minute, empty product of irreducibles times a unit. I'm allowing irreducible factorizations to include a unit so that I can get those plus and minus coefficients as I need to. All right, so that's my base case. Let's do one more base case just because I always feel suspicious of any induction that reduces down to the degree 0 case. If degree of Q of x is 1 and Q of x is primitive, then I claim Q of x is irreducible. Certainly it's not a unit, because how are you going to multiply a degree 1 polynomial by anything and get back to a degree 0? Not going to happen. So it's certainly not a unit. So if it did factor, if it equaled a of x times b of x, with a of x and b of x both non-units, well, since the degree of Q of x is 1, that would mean that one of these has to have degree 0. Otherwise, they'd both have degree at least 1, and that would force Q of x to have degree greater than what it actually has. So if a of x and b of x are both non-units, then a of x or b of x has degree 0. But then since we assume both of these are non-units, they can't be plus or minus 1. And now we run into a problem because that means that Q of x is a product of some polynomial with a polynomial that is an integer greater than 1 or an integer less than -1, which means q of x is going to have content. But then q of x has content greater than 1, which is a contradiction. Okay, so that means q of x has to be irreducible. All right, so that's the base case. That's a generous amount of base case there. I think that ought to be enough. All right, so let's see if we can get the rest in this frame here. So for the induction step, actually the induction step is not so bad once you've accomplished the rest. If you've set the induction up the right way, for this proof the induction is not too bad. All right, so let's assume any primitive polynomial of degree less than k is factorable into irreducibles. All right, so let's assume that. And let's let q of x be primitive of degree k. All right, then what are we going to do? Well, first of all, if q of x is irreducible, then we win. It's already factored into irreducibles. So if q of x is irreducible itself, we are done. Because our goal was to factor into irreducibles, and, well, that's already done. If q of x is reducible, which is the only other possibility here, it can't be a unit because we are sort of tacitly assuming here that k is greater than 0. I'm assuming that because I've already addressed the case in which k is equal to 0. So we're going to assume that the degree k is greater than 0, which means q of x can't be a unit. We're assuming it's not irreducible, therefore it must be reducible. So if q of x is reducible, then q of x is equal to a of x, b of x for some non-units, a of x and b of x. And now we're going to run the same argument that we did with degree 1. If either of these had degree 0, we'd have a contradiction. So if either a of x or b of x, and just for ease of communication, let's say a of x, were degree 0, then since it's a non-unit, it would have to have some prime divisor. P. But then that P would also have to divide q of x, because q of x is a of x times b of x. So P would divide the content of q of x, and that would be a contradiction since we assumed q of x was primitive. Okay, so what does all that mean then? So that means that a of x and b of x, neither one of those can have degree 0. So degree of a of x and the degree of b of x both have to be greater than or equal to 1. And now that means since the degree of q of x has to equal the sum of those degrees, degree of a of x plus the degree of b of x, sorry about that, it's a little squished there, that means that each of those degrees has to be less than the degree of q of x. So the degree of a of x and the degree of b of x both are less than k, which means they're subject to our induction hypothesis. So both factor into irreducibles. And because those both factor into irreducibles, that means q of x, which is just a of x times b of x, that means q of x can be written as the irreducible factors of a times the irreducible factors of b. So q of x itself factors into irreducibles. And that's the proof pretty much. Okay, so what does all of that mean? Let's zoom out. So what all of this shows, we're not exactly done yet. We've proven that every primitive polynomial factors into irreducibles. We do have a little more to do though. But here's what we know. And this is now coming back to our preamble here. So now what we know is that p of x, that primitive that we had earlier that came out of f of x, it factors into irreducibles. And we also know that d, because d is an integer, it factors into prime numbers. In other words, it factors into things that would be irreducible in Zx. So that means that f of x, which is d times p of x, is the product of some irreducible integer factors, possibly none of them, maybe a unit there in the content, and some irreducible polynomial factors of degree greater than or equal to 1. I don't want to exclude the integer factors from being polynomials because they actually are polynomials in Zx. It's just here I mean polynomial factors of degree greater than or equal to 1. Okay, so therefore f of x factors into irreducibles in Zx. In the next video, we will show that factorization into irreducibles is unique up to the usual caveats.